Hello, everyone. Want to tell you I hope you're having a good day, and I hope that the week is going well. We're going to talk today about finding segment lengths in circles. This is section 10.6 out of the book. This is a section that was omitted from the Unit 5 Mastery Test, and will continue to be omitted from that test, obviously, but it is an important set of theorems in and of itself. We're going to talk today about the simple idea that if we take a look at circles and we think about the lines that come into them, we can actually start talking about the lengths of them. Every other theorem that we've discussed has to do with the angles and the arcs and the measures of those, but there's a way that we can actually look at those lengths. Now, one of the things that I want to say right off the bat, which is kind of an interesting side note, is that these theorems were not part of Euclid's Elements. All the other things were. The fact that we have arcs that are formed by inscribed angles and central angles, the fact that if I have two lines that intersect inside a circle, the measure of the angle is equal to half the sum of the arcs, all those, that was part of the Elements. These theorems are not. These theorems were done by a guy named Jacob Steiner, who was a mathematician in the late 1800s who chose to prove everything that he did in what we call a synthetic way. And why they call it synthetic, I honestly don't know, but basically the idea is that there are two kinds of proofs. There are ones that are called synthetic and ones that are analytic. We've discussed this before, but even though in the late 1800s analytic proofs have been long the fashion, Steiner still chose to do everything in a synthetic way. So we're going to take a look at these theorems. I'm going to show you one proof, but I wanted to throw that out to you before we got too far. All right, we have a couple of definitions. The first is the segments of a chord. These are the line segments formed when a chord is divided into two or more pieces. Now, one of the things I will tell you as we get going here is that I'm not going to give a lot of time for you to write these definitions down. Instead, you should be writing the terms, and then you can go back in and get the definitions out of your text. The segments of a chord, to let you know, are these pieces. So if I think about chord AD, and then I think about chord CB, because E is this point of intersection, that actually means that there is a segment of the chord AD, and those segments are AE and ED. I also have a secant segment. Right? The idea behind a secant segment is that if I go in and put a secant, then that secant, because it goes through the circle, can be split into two parts. The secant segment, which is the part of the secant that's inside, GH here, and then what we call the external segment, and that's, as obviously the name indicates, the external part, the exterior portion, in this case, FG. All right, we have a theorem, theorem 10.14. Again, just write down the theorem number, and then you can go back in and write down the text. The idea behind this theorem is that if I have two lines that intersect inside of a circle, we know that the length from A to E times the length from E to D is equal to the length from C to E times E to B. Again, these were not part of Euclid's Elements. This is a pretty interesting concept. Steiner called this the power of the point. And in fact, what we're going to do is we're going to take that point of intersection and move it around and create different options as far as the different kinds of segments that come together. But again, for this, two lines cross on the inside simply means that this portion times this portion is equal to this portion times that portion. Let's take a look at an example of this. So, if we have this circle, we should notice that this portion is x plus 1, this portion is x plus 3, we've got 3, we have x plus 5. So, the theorem tells me that this portion times this portion is equal to this portion times this portion. So, x plus 3, x plus 1 are multiplied together, and 3 and x plus 5 are multiplied together. Now, at this point, geometry is over, algebra ensues. Left side gets multiplied out to be x squared plus 4x plus 3. Use your box method if you need to. The right side becomes 3x plus 15. From here, we're just solving. Move the 3x and the 15 to the other side. And we have x squared plus x minus 12 is equal to 0. This is a box method problem, and we get x plus 4 times x minus 3 is equal to 0. And at that point, we can solve. Now, one of the things that we have here is a situation where these algebraic statements have a geometric significance. So that means we need to plug back in to make sure that they actually work. Here, if I take negative 4 and plug it into this statement there, I've got negative 4 plus 1, which is a negative number, negative 3 to be exact, and that can't happen. That would give us a negative segment length, so we know that the negative 4 is in fact a bad value. So our answer is just 3, which we could just verify by looking at those two segments, 3 plus 1, 3 plus 3, and then 3 plus 5. Now again, one of the things that we should notice is that as soon as we write our first statement, the geometry is over. And now we're just testing ourselves as far as our understanding of algebra. Let's do another example. Same idea here. I've got x and x plus 10 and x and 14. So x times x plus 10 is equal to 14 times x. This problem ends up being a little bit easier than the last, although the last one was pretty straightforward. We multiply out, and then we can start solving. We're going to move that 14x to the left side. And from here, we're going to factor out the x. And then we will solve. So here we get x is equal to 0, x is equal to 4. And obviously, if we look at this statement, x cannot be equal to 0, so we know that we can cancel that out. All right. Now, I want to take a look at the proof of this theorem, just because it is kind of an interesting one that really doesn't involve much more than everything that we've already seen. All right, so first step of this proof is that we need to construct segments AD and CB. Remember, our end goal is to get this piece times this piece is equal to this piece times that piece. But we have to take this first step, so we construct those segments. All right, now, what we should notice here is that we have an arc here that is formed by this angle and this angle. And then we have this arc that is formed by this angle and that angle. So, that means that because these two angles form the same arc, they have to be congruent. And because these two angles form the same arc, that has to be congruent. So we have this statement. Now, if you think about our methods of proving triangle similarity, angle was one of them, and lo and behold, we have enough information to prove that triangle DAB and triangle DCB are in fact similar. All right, now, what we are able to say, because of the fact that we can say that those two triangles are similar, well, we've got AE over CE is equal to ED over EB. We're able to write that out as a proportion. And from there, we solve out. Now, this seems like an odd result from this statement. But if we took AE times EB, just like we were cross multiplying, and CE times ED, we would see that relationship. All right, let's take a look at the next theorem. This theorem is based on the fact that I may have two secants. All right, so the last theorem had us multiplying two segments together. That's what we're seeing here, except it's slightly different. what we actually see is that if I have two secant segments, this portion, the external portion, times the whole thing is equal to the external portion of this one times the whole thing. Okay? So again, outside times the whole thing is equal to outside times the whole thing. Alright, let's take a look at an example. Alright, in this case, we have two secants, so that means that this portion times the whole thing is equal to this portion times the whole thing. So, that is 3 times x plus 3, which is the whole thing, and 4 times 5 plus 4, which is the whole thing. Just like before, geometry is over, algebra ensues, so that means that I'm just going to solve, distribute that 3 in, get 3x plus 9, and then on the other side here I've got 5 plus 4, which is 9, times 4 is 36. Move the 9 over, I got 3x is equal to 27, and x is equal to 9. I check to make sure that this will still work, because this statement does have geometric significance, and x is equal to 9. We're good. Alright, last theorem for us. This theorem says, basically, that if I have a tangent line and a secant that intersect outside the circle, obviously a tangent line has to be outside the circle, excuse me, what we notice is that this length, that external tangent line length, squared, is equal to this portion times the whole thing. So, again, this portion, the tangent piece, squared, is equal to the outside times the whole thing. Let's take a look at an example. I have to apologize, this is incorrect. We're trying to solve for x here. Okay, so I've got a tangent line and I have this secant. So what we said is that this portion squared is equal to this times the whole thing. So outside portion x, the whole thing, x plus 8. This portion, of course, is 16. From here, we solve. I distribute that x in, move the 256 over so I'm equal to 0. And at this point, I should notice that I have no numbers to multiply together to get to negative 256. Add to get to 8. So, we use the quadratic. Negative b plus or minus b squared minus, radical b squared minus 4ac all over 2a. In this case, our b is 8, so this becomes negative 8. 8 squared. Our a is 1. Our c is negative 256. And down here, because a is 1, this is just 2. Put all this together and we get 1088. Now, one of the things that we should notice is that this is a positive length. If we went through and added, added a negative 8 to radical 1088, we get a positive number. But if we took negative 8 minus radical 1088, obviously we get a negative number. So technically we end up removing that negative out of there. Now, one of the things that I will tell you is that if you are going to simplify, make sure that you are doing it carefully. In this case, 1088 reduces down to 8 radical 17. And from there we can reduce it to negative 4 plus or minus 4 radical 17. Again, we make sure that we're very careful as we do that. Last thing we want to do is to make a silly mistake on something that is a fairly obvious thing. Okay. From here, here's your homework. 10.6, 2 through 12 even, 13 through 18, and 20. Hope you have a good rest of the day. Thank you.